Okay, let's just dive right into this explainer and actually look under the hood of AI. We want to see how we give machines literal, real-world superpowers. We hear a ton about artificial intelligence generating text or playing video games. But today we're looking at how machines actually learn to interact with the messy physical world around us. We're going to explore the cutting-edge algorithms making autonomous robotics possible, how engineers even begin to troubleshoot them, and, of course, the massive responsibilities that come with wielding this kind of power.
Section 1. The Upside-Down Helicopter. We're starting off with a pretty magical and honestly slightly terrifying real-world application.
Picture this. A few years ago, Stanford researchers were testing a small autonomous helicopter over a soccer field. Their goal was to see if an AI could pull off aerodynamically impossible stunts using reinforcement learning. And to give you a sense of just how wild these aerobatics were, an elderly neighbor in a high-rise right next to the field actually called 911. She literally told the dispatcher that a helicopter was tumbling out of the sky and about to crash. The fire department rushed out, only to be, well, partly relieved and probably partly disappointed that there was absolutely no one to save.
Because the punchline here is that it wasn't crashing at all. The AI was flawlessly executing what is known as a chaos maneuver. This helicopter was turning upside down, spinning around, in literally every single direction, but perfectly maintaining its exact place in the air without dropping an inch. It was using reinforcement learning to pull off moves that even the absolute best human pilots on Earth struggle to do.
Moving to Section 2. Debugging the AI brain. How in the world do we fix these machines when they fail?
Because to stop machines from just immediately crashing in the real world, AI engineers have to go through this really grueling, iterative reality check. When an AI first flies, it's terrible at it. So to debug it, they run through a strict three-step checklist. First up, you check your simulator. If your AI flies beautifully in a computer simulation but faceplants in real life, your simulator is inaccurate. Second, you check the algorithm itself. You basically pit the AI against a human pilot, and if the human is getting a higher mathematical reward than the AI, well, your algorithm isn't maximizing the reward properly. And third, you check the reward function itself. If the AI gets a higher mathematical score than the human, but still flies like garbage, it means you're rewarding the wrong behaviors.
So the absolutely crucial takeaway here is that building AI is this constant, never-ending loop of moving bottlenecks. It's like a giant game of whack-a-mole. Fixing the simulator might take you 2 whole months, but once you finally fix it, that just exposes that your reward function is actually flawed. So then you spend another 3 months fixing the reward function, which then exposes that your algorithm needs work. You are just constantly iterating, exposing the next biggest problem until you finally get a machine that can actually hover upside down.
Section 3. Direct Policy Search Explained. Let's look at the secret weapon engineers use to conquer these crazy robotics problems.
Traditionally, AI relies on this indirect method called value iteration. That essentially means the computer tries to estimate the mathematical value of every single possible state in the world before deciding what to do. But with direct policy search, we skip the middleman. Instead of doing the exhausting, mind-numbing math of mapping out the entire environment first, we just go straight for finding a good rulebook or a policy for taking action right now.
Now, what's super interesting about this method is that the AI doesn't pick rigid, binary actions. It uses a stochastic policy, which is really just a fancy way of saying the algorithm outputs probabilities. Think about balancing an inverted pendulum. The AI doesn't just confidently declare, go right. Instead, it looks at how far the pendulum is tilting and says, okay, there's an 80% chance I should heavily accelerate to the right, and maybe a 20% chance I should go left. It's incredibly fluid.
And it learns all this fluidity using something called the reinforce algorithm. The machine essentially takes millions of slightly noisy, completely random steps. After every sequence, it computes its total payoff. It then takes those internal parameters and updates them to slowly climb the gradient toward a higher reward. Honestly, it's a wildly inefficient process, often requiring millions of iterations. But mathematically, it perfectly climbs the hill toward total mastery.
Which brings us to Section 4. Dealing with partial information.
Because out in the messy real world, we run into the massive obstacle of inaccurate, noisy sensors. Imagine that inverted pendulum again. You've got an angle sensor that works perfectly, but oops, your speed sensor is completely broken. You are getting noisy, incomplete data. You are essentially flying completely blind. In the AI world, this nightmare scenario is called a POM-DP, a partially observable Markov decision process.
Traditional value estimation algorithms totally break down in this scenario.
I mean, if you don't know your exact state, how can you possibly calculate your exact value? But direct policy search, it naturally solves this. Because it's just looking for a simple rulebook based on available inputs, you can feed those noisy, partial observations directly into the policy. It literally just learns to make the best possible probability guess with the broken tools it has. It's brilliant.
Section 5. Choosing the right algorithm. So as an engineer, when do you use which tool? Well, there is a massive divide in AI logic. On one side, we have seat-of-the-pants tasks. These are low-level, totally instinctual control actions, like a human hovering a helicopter by feel, or just subtly tapping the steering wheel to stay in your lane on the highway. Policy search is perfect for that. On the other side, we have multi-step reasoning. This is high-level planning. Think of mapping out 10 moves ahead in a game of chess, or calculating exactly how to pass a semi-truck on the highway before another car merges. For those tasks, you absolutely need value function estimation. And if you want to build the ultimate, world-beating system, you combine both. That is exactly what DeepMind did with AlphaGo. They blended direct policy search to give the AI this instinctual, almost human feel for the board, and ran it alongside value functions for that deep, multi-step planning. That specific combination is what allowed the AI to achieve truly superhuman performance.
Finally, Section 6. With great AI power comes, well, a lot of real-world impact.
Because these algorithms, we aren't just doing helicopter stunts with them anymore. They are being applied to massive, sequential, real-world problems. We are seeing reinforcement learning optimize massive factory floors. It's being used to map out complex, multi-step healthcare treatment plans, like tracking how a patient reacts to a blood test, then a biopsy, then a trial drug over the course of months. It is even being used in dark pools to stealthily trade millions of shares of stock without alerting the broader market. This stuff is everywhere.
But as the renowned AI researcher Andrew Yang points out, deploying these systems at such a massive scale comes with some really serious consequences. He noted that years ago, the contract Silicon Valley had with society was basically, you trust tech with your data, and tech will use it to help you. But today, that faith is deeply shaken. There's a growing realization that some of these exact same machine learning algorithms have been optimized purely for profit, leveraging our human tendencies just to maximize engagement rather than actually pushing humanity forward.
Understanding how an AI decides to act, whether that's flying a helicopter upside down or managing a patient's care, gives us incredible insight into the future of our world. You now understand how these powerful machine learning systems actually work, right down to the algorithms and the debugging. So the only question left for us is, how will we use these superpowers? Will we exploit the system, or will we build something that genuinely benefits humanity? Keep that in the back of your mind the next time you interact with the algorithms shaping our lives today.